B along B dot delta L along B plus B along C dot delta L along C plus B along D dot delta L along C is going to be equal to mu naught epsilon sub naught d dt of E dot A. So in my segment A, my line is going up. My line integral is going up. My magnetic field is going up. So they're going in the same direction. So this is just going to be B times H. In segment B right here, my line integral is going to your right. My magnetic field is still going up. So what is this equal to?
0.
Along C, my line integral is going down, but my magnetic field is going up, so minus B plus dV times H. And then plus 0 again, because in the bottom segment, my magnetic field is still going up, but my line integral is going to the left. And that's going to be equal to mu naught epsilon sub naught. E and A, same direction, so area vector is constant, so I end up with A times d dt. Over on the left-hand side, if I have a couple ways of doing this one. If I distribute the H, the BH disappears, and I'm left with negative H dB is equal to mu naught epsilon sub naught by area H dx times d dt. H cancels out. And similar to what I did before, we get negative dB dx is equal to dE dt. Let's see what that yields us. Questions before I turn the page? B was B sub m cosine of kx minus omega t plus phi is equal to ddt of my electric field, which is E m cosine kx minus omega t plus phi. So what's my left-hand side equal to?
Just BMK cos their sine kx minus omega t plus phi.
And on the right-hand side? No. We're taking the derivative of this with respect to time.
E omega, and then sine of kx minus omega t plus phi.
If you're concerned about the negative signs, the derivative of cosine gives us a negative, which cancels out with that negative. Over here, the derivative of cosine gives us a negative sign, but when we use the chain rule and do the derivative of this, we get a negative omega. Those negatives cancel out. Again, we are now left with, I left something off here, very important. That's equal to mu naught epsilon sub naught. I'm just going to flip to the other page. Yeah, I dropped it at this point. That doesn't go away. That's rather crucial that that's there from mu naught epsilon sub naught. So mu naught epsilon sub naught. So if this is true, always true, then BMK has to be equal to mu naught epsilon sub naught E in omega. Again, I'm trying to find the speed of a wave here, so I know the speed of a wave is omega divided by k. And so, see, k comes there, so I get Bm over mu naught epsilon sub naught E sub m. That's got to be equal to what we have over there, which is Em over Bm. Unless we made a mistake somewhere, but what we got derived before has to equal what we derived just now. So if we do that, I get 1 over mu sub naught epsilon sub naught equals, just getting all my magnitudes over on the right-hand side, or my amplitudes, I get Em squared over Bm squared. Bringing that up and that down. And from this, if I take the square root of both sides, I get Em over Bm is equal to the square root of 1 over mu sub naught epsilon sub naught, which, and Em over Bm is just the speed of the wave. So Maxwell derives the speed of an electromagnetic wave. Well, we pretty much have values for that stuff, so we can do the calculation now. And that will not work on this board. Mu sub naught, 4 pi times 10 to the negative 7th Tesla meters per ampere. Epsilon sub naught, 8.85 times 10 to the negative 12th. That should be Coulomb squared per Newton meter squared. And if we plug into that formula for the speed of this wave, what do we get? I guess you forgot to take the square root.
Yeah, 2.999 times 10 to the 8
Units?
Meters per second.
Yep. Of course, given those units. All right, so we have the speed of an electromagnetic wave. Two things. One, Maxwell notices that this is really darn close to the measured speeds of light. There have been various attempts to find the speed of light. Galileo tried it. His method was the lantern method, where he figured human reflexes would be constant, and so he was on one hill, a minion was on another hill. They lifted up the lantern and then so they exposed the lantern, put it back down, exposed the light. The person on the other hill would see the light and do the same, and so they'd measure that time, then they'd go farther apart and do the same thing again, assuming that the human reflexes were the same both times. You would get a value for the speed of light, and came to the conclusion that if light is not instantaneous or infinitely fast, it is very, very fast. That's as best as Galileo could get. This was later improved upon by shining light against a mirror, and eventually a bunch of mirrors so that you can get a farther distance, and you basically get a cog with a bunch of teeth in it, and you start turning it. And so if you're turning it slowly, light's going to go between two of the teeth, hit the mirror, bounce back, and you would still see it. It goes faster, suddenly it's going to go down. When it comes back, it's going to get hit by the next tooth in line, and so you won't see it, and turn it even faster. You'll see it again as it appears over here. At that point, you figure out how fast this thing is rotating, you know how far the light travels. If you know how fast it's rotating, you can get the time between the gaps in the teeth, and you calculate it that way. And they had a value very similar to this. So Maxwell makes the jumps, speculates, doesn't jump to the conclusion, he speculates that too much of a coincidence, light, he suspects, is an electromagnetic wave. Also, recognize that the whole idea of electric fields and magnetic fields, they had no idea if that was actually had any physical meaning whatsoever. It was a mathematical convenience for the previous however many decades. This is the first big piece of evidence that says, yes, electric fields and magnetic fields really do exist. It's not just a mathematical convenience. Questions before I ask a question of you? Maxwell denotes the speed of light as the letter c with the formula of the square root of 1 over mu sub naught, epsilon sub naught. So that would be the speed of light in a vacuum. Physicists have looked at this and said that is really incredible work. However, there's a mistake. Why would someone look at that formula for speed and immediately jump to the conclusion that there's something missing?
Is it unit related?
Is it?
Is it unit related?
No, it's not a unit issue. I will say that the fact that Maxwell had not made a mistake will kick off one of the great revolutions of physics. What do you know about speed? Besides distance over time, or dx dt, however you want to do it.
It doesn't have a direction.
Okay. How fast are you moving right now?
It's relative to where you're at.
In this equation, where does the speed of the observer show up?
Nowhere.
And that was what was speculated, is there's something missing. This is great work, except for the fact that you have nothing in here about the observer. Lorentz, one of the great physicists of the late 19th century, spent a long time trying to figure out why it doesn't show up. But he could not make that leap that would have solidified him and pushed Einstein as not as awesome as he ended up being. Lorentz came up with all the math for what Einstein used later. Well, I shouldn't say all the math. A great deal of the math that what Einstein came up later. But Lorentz couldn't make the leap about what this is actually saying about the speed of light. What this says about the speed of light is that the observer does not matter. The speed is the same. That is an incredible breakaway from what was thought before. It was thought before that time was constant for everybody. Einstein comes up with the following thought experiment. Or for the anti-Einstein people, his wife came up with it. There's debate about how much his wife contributed. He thought of the following Gedanken experiment, basically thought experiment. I have a mirror here, and we'll call this the lab frame. And I have a box moving to the right at some speed v. As it's moving to the right, it's going to shoot a beam of light upwards. and it's gonna hit the mirror, but there's a sideways component to it, so the light's basically gonna do this, and then come back down, and it's gonna hit the box again. So the lat frame, light's shooting to the right, light comes up, bounces against the mirror, hits the box again. In the box frame, if you're in the box, what you see is the light just goes up and comes back. So two different points of view here. We'll just make this distance here h. So if I want to figure out the speed of light in both of these cases, I just do distance divided by time. So this is going to travel at some spot, try it this way. This is going to take some time t, and so the box is basically going to travel a distance dt. Here the box is not moving at all. And so, well, if I look at that triangle there, I got a right triangle. I know the height is h. I know the base here is half this distance, because I'm looking at basically half that triangle there. So this is 1/2 of vt. And the distance that it travels here, well, it's traveling at the speed of light for some time t, and that's half the journey, so 1/2 ct. Pythagorean theorem holds true. I have 1/2 ct squared equals h squared plus 1/2 vt squared. I want to do that slightly differently. No, I'll keep it at that. Down here in this reference frame, the speed of light is going up and back, so the distance it travels is 2h over time t. In this frame right here, it's going this distance right here, again, do a little Pythagorean theorem. In this frame up here, we have the speed of light. The distance it's going to travel is 2, because it goes up and then back down, of the square root of h squared plus 1/2 vt squared over time. If these two things are equal to each other, what else has to be true? If the speed's the same and the distances are different, if you and a friend are both going 50 miles per hour, and you go 100 miles and your friend goes 150 miles, what's the difference between the two of you? Yeah. In that scenario, when you traveled for 2 hours, your friend traveled for 3 hours. Same is true here. The time cannot be the same. If this is true, if the speed of light is constant, the time cannot be the same. And so we're going to put a little subscript here to differentiate it. I'm going to put a little p there to represent what is known as proper time. From this equation right here, h is equal to 1/2 CTP. So I'm going to plug that in for h. So that first line right there, sort of ignore that. So I have CT, let's see, multiply by t, divide by 2. So 1/2 CT is equal to the square root of 1/2 CTP squared plus 1/2, put the parentheses in the wrong spot, 1/2 VT squared. I got a 1/2 in both terms. I can factor that. I got a 1/2 squared. I can factor that out, take the square root. In essence, my halves go away. So I get CT is equal to the square root of CTP squared plus VT squared. Now I'm going to square both sides. So I have the speed of light squared times time squared in the lab frame is equal to speed of light times the time in the proper frame, or the box frame, c squared, plus v squared, t squared. Again, that's the speed of the box in the lab frame, and that time right there is the time in the lab frame. I want a relationship between the times, and so I'm going to subtract this over to the other side, so I get c squared t squared minus v squared t squared equals c squared tp squared. Because I know what the final form is that I want, I'm going to divide by c squared. So I'm left with t squared minus v squared over c squared t squared is equal to tp squared. Factoring t squared out, I get 1 minus v squared over c squared. T squared equals tp squared. Taking my coefficient here, dividing by it to get on the other side again because of the final form that I want, I get t squared is equal to the proper time squared over 1 minus v squared over c squared. Square root of both sides, and t is equal to the proper time over the square root of 1 minus v squared over c squared. That is the time dilation formula. So if I have an object traveling at a certain speed, and I make it go faster and faster and faster, what happens when the speed equals the speed of light? When v equals c, what happens?
The time disappears.
In essence, yes. If v equals c, we get the division by 0. This tells us that nothing starting slower than the speed of light can actually get to the speed of light. Now, someone else looked at this and said, it also would mean that something that starts out faster than the speed of light can never go slower than the speed of light. Now, how do you actually find those particles? Well, there's a theoretical particle called the tachyon. If tachyons exist, then